Swayam Prabha. Digital India. Educated India.
This morning we talked about force modeling, lots of details. Maybe you may have heard of BBOE equation, Maxi-Rally equations. So you learned a lot more about the details of what goes in there. Okay. I want to start this afternoon with particle turbulence. Okay, so we are getting a little bit more. So here, obviously, since the word turbulence comes, so nothing is going to be analytical. No, it's mostly empirical. Okay. There are two questions you will or you can think about: how particle creates turbulence. That's one thing. The other is how turbulence changes the particle. Both of them are important, and I want to I have several lectures on that because it's a very important topic. Now, I should point out that everything I will say is with regards to individual particle. So, in other words, I will not talk about particle-particle interaction yet. We are not ready for that. Okay, we are going to. We earlier saw forces on single particle. Okay, sort of continuing on that. Now we say, okay, let's look at turbulence and see how multiphase turbulence, how particle will change fluid turbulence. How fluid turbulence, we already talked about, it can demix. It can mix as well as demix. How does that work? Okay, so those are the things that I want to talk about today. First, I want to talk about if you have a single particle and you have a flow coming towards it, uniform, steady flow, what about the wake of the particle? Okay, so that's what I want to cover. And there are two papers by Tiwari and collaborators, excellent review papers on this, and I'm just literally going to repeat what they have said in their paper. Okay, so their papers are like 60-70 pages, and I'm going to give it to you in 20 minutes. Okay, so you don't have to read that paper in detail. I want to summarize it for you. So the thing is that we talked about Reynolds number. Reynolds number is diameter of the particle, which I've been using the term, and the relative velocity between the particle and the surrounding fluid times kinematic viscosity. Sometimes I have been putting this subscript f. So this is the only knob. Think of it this way. So if you have mounted a sphere in a wind tunnel, the only thing, so particle is not moving. In this case, I'm going to freeze the particle. I'm just cranking up the velocity, so as to speak. Okay. Now, what happens is that you may be familiar with when Reynolds number really small, we are in the Stokes regime, and you have no separation, nothing. As you increase the Reynolds number, the flow bifurcates, goes through many different bifurcations, and I'm going to list them. And you go from regime 1 to regime 2. Around Reynolds number 1, it just, you don't have any separation till about 22 Reynolds number. The flow just attaches back, and here. Now between 22 and 210, you have what is called a steady axisymmetric wake. There is a bubble, wake bubble behind that. And at Reynolds number 210 to 270, I don't know whether you are familiar, the axisymmetry breaks down, and you only have planar symmetry. So the wake sort of tilts to one side. Okay, so in fact, if you drop a sphere till about 210 Reynolds number, it will fall vertically, but afterwards it will sort of go to one side, okay, because it becomes a one-sided wake. It just natural bifurcation happens. So axis symmetry is broken and it becomes a planar symmetric wake. But all these four regimes are steady. There is no vortex shading yet. Vortex shading starts at Reynolds number 210. So these are how the flows look like. So the difference between R1 and R2 is at very low Reynolds numbers, left side and the right side are the same. So it's perfectly front back symmetric. That's the property of Stokes flow. Now when Reynolds number becomes non-Stokesian, it still remains attached, but the front back symmetry is broken. So you can see the streamline, the way it comes towards and the way it leaves are not perfectly symmetric. About 22 you have a eddy, and that eddy gets bigger and bigger. And then I said that about 210 you get this bifurcation where the flow becomes one-sided. So you can see from the side there is only a vortex thread. It's a double threaded wake. Okay, so that's what they call it. Now if you further increase the Reynolds number, it becomes periodic, sinusoidal, shedding vortices between 360, and up to here you can say the wake is laminar. Okay, up to Reynolds number 360 it's laminar, and you can calculate lots of things like what's the length of the wake bubble. Of course up to certain Reynolds numbers there is no bubble, but afterwards it starts increasing in regime 3, regime 4, regime 5 there is a wake. Okay, and separation point. So there's a lot of details that are in the paper. But then what happens when you go above Reynolds number 360 up to Reynolds number of 3000? It's not perfectly periodic, it's not sinusoidal, it becomes chaotic vortex shedding. So in other words, best way to think of like you putting a velocity probe in the wake and making measurements. Till 360 it will be nice sinusoidal curve, and afterwards it will be quasi-periodic. Yes?
So could you please give me one simple example in which or two regimes will come in capture?
I cannot hear you.
Could you please give one simple example in which we can see by varying these Reynolds number we can achieve?
We can
change? By changing the various Reynolds number, different flow region we get, Stokes flow region and separate flow region. Could you please give me one example?
One example where all these Reynolds number. So it's not going to be that way, right? You may have an example where Reynolds number may go from very low values maybe to maybe 1 or 2. In another problem it could be, it may start from Reynolds number 1 and it may vary between 10.
Miniature channel where single particle, miniature micro channels. In
micro channels all the Reynolds number will be very small. In say fluidized bed it may go from 1 to few hundred. In say shock particle interaction where the Reynolds number could go from few hundred to few 10,000s. Okay, and if you are looking at cricket ball or golf ball, Reynolds number go to a million. So I'm just trying to see different problems, different regimes as the Reynolds number changes, just giving you an idea how the flow is likely to be different, how Reynolds number plays an interesting role. As you change the Reynolds number, as the inertia of the flow increases, you see all these kind of fascinating bifurcations. So it's basically these fluid mechanics phenomenon. Okay, not in one application you are not going to see everything. Okay. So here what I meant by chaotic was, if you look at the drag or lift coefficients, you can see as with the increasing Reynolds number. So what's being plotted is that in this case is force on the y direction and force on the z direction. Okay, so in other words, x is the flow direction, the forces drag coefficients on the other two directions with increasing Reynolds number. This is the one-sided wake that I talked about, where there is a lift force, but the lift force is very, as the shedding happens, you get nice periodic kind of signature. But with Reynolds number increasing, you see the lift force, which way the particle is going to be pushed, is just chaotic. It just executes all sorts of complex stuff. Okay. Now, the shedding, see here also another thing that I want to point out is that you can clearly see that when Reynolds number of the particle is fairly large, it's creating turbulence. Okay. Because as you can see in this picture, the flow that comes on is uniform, but it's creating a lot of vortices. Therefore, as he points out, this may not be a big issue in microchannel with small particles, but if you have fluidized bed and where you have lots of dynamic motion, now the particles, each particle themselves is a creator of turbulence. Okay, while it may also be damping turbulence, is producing a lot of turbulence. Okay, and certainly in shock particle interaction or high speed flows, you can have a lot of turbulence being created by each particle themselves. Now, Strouhal number is very important because somebody asked, so this turbulence I call it pseudo turbulence in a way, okay, because it's particle generated turbulence. Okay. Now, if you use sort of like isotropic turbulence or wall turbulence, it follows 5/3 spectra, Kolmogorov theory, and so on and so forth. Clearly, this turbulence is going to be a little different because in isotropic turbulence, you don't know of a very particular frequency. I mean, every frequency is there, right? But if we all know at the same time that vortex shedding happens at specific frequencies. Therefore, this turbulence may have a dominant frequency. So, one needs to be very careful in terms of modeling particle generated turbulence. Okay. So, this paper, Tiwari's paper, very beautifully characterizes everything, what the shedding frequency in the different regimes and so on. So, right now so far we have only covered I6, where I used the notation R means regular, I means irregular. So, irregular regime 6 is up to a Reynolds number of about 3000. Now, what happens is that when Reynolds number increases, as the Reynolds number increases about 3000, the wake becomes turbulence. So, you can see still the particle which is in here, its boundary layer and some distance downstream the flow still looks very smooth, but downstream becomes chaotic. This is about at 3700. Now, if you increase it to 10,000, the turbulence has moved up. So, with increasing Reynolds number, the turbulence will move upstream. Your shear layers will become unstable. Then it will get closer and closer. As you can see, this is 2 times 20,000, 100,000, and this is 1.14 million. Yes.
Sir, in the traditional fluid mechanics, we study that the flow becomes turbulent in case of flow through pipes if the Reynolds number is more than 2300, and in case of flat plates, if its Reynolds number value is more than 10 to the power 5. Then why is the motion getting chaotic at only this much 200 or 400 value of Reynolds number?
Here, why does it become unstable even at Reynolds number 200? Yeah. Well, the thing is that in a pipe flow or in a boundary layer, there is no recirculating region. Okay. Therefore, they are what are called convectively unstable. In fact, the numbers you quote are not fixed there. If you have a channel and you can make it quiet, what they call it quiet means if you reduce the upstream disturbance that is coming into the tunnel, you can keep it laminar for a long time. Okay. So, in other words, there whatever you see in a pipe or in a channel is convective instability. It will become unstable, become turbulent, etc. But in contrast, the wake behind a particle, all these things are absolutely unstable systems. Okay. So, in other words, that recirculating thing is sort of like once the disturbance starts, it will never stop, because it retains a little bit of it inside to feed continuously. So, therefore, the bifurcation here, for example, this 210 when the flow or 270 when the flow becomes unsteady and starts shedding is fairly robust. Okay, and 360 you get other kind of bifurcation that I talked about. They are very very definitive. So, because of the absolute nature of the instability. So, the wake becomes unstable at around 3,700 or something like that, but that stays only maybe couple of diameters downstream. As you increase the Reynolds number, closer and closer to the particle becomes turbulent, the immediate wake becomes turbulent. And you can see from this picture, you really have to go to 10 to the power 5 and above for the attached boundary layer to become unstable. Okay. So, I do not know how many of you have heard of drag crisis. The drag decreases in this case when Reynolds number increases, because you can see the difference between from here to here. Here, the attached boundary layer is not turbulent, it is laminar, only the shear layers are unstable, so you get a big wake. When the attached boundary layer becomes turbulent, separation is delayed, and this is why golf balls are dimpled. The golf balls are dimpled because they want to operate in this kind of a mode. The drag is low. So, they purposely make the surface rough to make this happen. And why does a cricket ball does it is they do a very clever thing. Imagine a situation where one half of the ball is very rough and the other side of the ball is not so rough. So, half a ball will have a wake like this, and half the ball will have a wake dampened. So, one side will have a bigger friction than the other side, and you will have a nice swing happening. That is why they keep rubbing it. I mean, you all know that. So, the reversing, the same thing for knuckleball in baseball. So, his question is very relevant in the sense that you are not going to see Stokes flow in a cricket ball, but the regime that you operate in golf balls and things like that is in this regime. Okay. Whereas, if you are doing table tennis and a ping pong ball, completely different regime. You cannot rely on turbulence at all there. It is mostly, I would not call it laminar flow, but it is a much more benign Reynolds number. Okay. So, every little physics is very interesting and people exploit it. They may not know fluid mechanics, but they know how to do a reverse swing. Yeah. Yes.
The contours are Twadding factor or elastic magnitude.
Just vorticity. Yeah, it just anything. I don't even know. But you get I just wanted to convey the visual picture.
The vertex shedding you have previously discussed. That is also vorticity, sir.
Yeah. This may be isosurface of vorticity at some magnitude. The important thing is that you can clearly visually see its turbulence. Okay. Yeah. And the turbulence moves upstream and enters the boundary layer. Once it enters the boundary layer, the wake becomes smaller and the drag falls down. Okay. And that is called drag crisis, and this is very well known. That exactly happens here, you see. Now, while the shedding of vortice is very definite, this attached boundary layer instability is convective instability. Therefore, where the drag crisis will happen will keep changing, whether you make the ball rough or smooth, etc. And that is why this drop may happen differently in different experiments. Okay? Because the attached boundary layers is a convectively unstable system. So, your upstream turbulence, your surface roughness, etc. will matter. Okay?
The drop is due to what, sir? Asked the drop, sir.
The drop is because of what I was talking. Before the drop, it looks like this. So, a big wake, a lot of drag, the drag coefficient is large, and the attached boundary layer is laminar. Okay? So, it does not now right here the flow looks more like this. The attached boundary layer has become turbulent. This is, by the way, is turbulent, but you do not see it because it's inside the boundary layer and it's a lot of turbulence. So a turbulent boundary layer separates later. Okay, it stays attached on the surface, so it just goes back on the back side and then only separates. Therefore, the pressure drag is much smaller here compared to here, and that's what you see here is in the. Okay. Now, obviously, in many multi-phase flows, you will never reach this higher Reynolds number. So this, I just thought that interesting thing about what happens of flow over a particle. Okay, but most of the fluidized bed, etc., you're not going to reach a Reynolds number of million, etc. So we don't have to worry about that. So just out of interest, I was showing. So that's the thing is that the one thing that I wanted to say is at higher Reynolds number, vortex shedding happens, and some sort of turbulence is created by the particle itself. So when we talk about turbulence modulation, turbulence being changed by the particle, you can now start seeing not one particle. If you have a million particles, all of them moving, each of them having shedding vortices, you have a lot of turbulence in there. Okay, and that turbulence happens at preferred frequency, which is the shedding frequencies and so on. Okay, so it's not going to be classical turbulence. Okay, the other thing is that you can see that there will be a lift force even without shear. Remember, I said that above a Reynolds number of 270, if you drop a particle, it's just going to go to one side. It will never fall straight. Okay, and that is due to the lift. And this lift is not due to a shear or rotation of the particle. It's simply because of how it shed vortices. Okay. So any questions on that? Now, yes.
So here I see that particles in some extent enhance the turbulence, right?
What is it?
The particles in some extent enhance the turbulence in this case. But if I consider, let's say, high turbulent flow initially, and if I consider sub-Kolmogorov particles, in that case, near the particles, the flow will not necessarily be a turbulent flow. It might be a slow flow also.
Yes. On the level of the particle, you will have low Reynolds number and you will have a damping effect on turbulence. Yes.
So in that case, I can say that particles is damping the turbulence.
Absolutely, absolutely. And also, it's an interesting point you raise is there is a relation between whether a particle is Kolmogorov size or larger. I will later, maybe on tomorrow or day after tomorrow, I will show some more details. When a particle is sub-Kolmogorov, Reynolds number is very likely to be less than 1. None of these things going to happen. Only when your particle gets bigger than the Kolmogorov scale, you're going to have all these scenarios. Okay, so that also one can do a very good estimate. I have a paper on that. If you are interested, I can share it with you, where we talk about what could be the most likely Reynolds number depending on the size of the particle in turbulence.
And one more thing, like, does it depends on the volume fractions of the particles? Like,
it is in some sense, but right now I'm dealing with what happens. We are just looking at one particle. Okay, so obviously, if you have many particles, one particle could be in the wake of another particle. So what is called wake-wake interaction may happen. Okay.
Like yesterday, you were showing the turbulence energy spectrum, and because of the modulation by the particles, that spectrum is changing. So, like, let's say I am operating in a volume fraction which is of the order of 10 raised to -2, -3. In that case, can I neglect that modulation?
Oh, probably not. Okay. If every particle is shedding like this, and even if you have 1% volume fraction, you may have plenty of turbulence created by the particles, right?
No, if the particles are sub-Kolmogorov, in that case,
then they will not create this kind of wake. Okay, if there are many 1% volume fraction, many particles there, but each of them creating not sub-Kolmogorov, they are bigger than Kolmogorov, Reynolds number few hundred, each of them shedding vortices as they are falling. Now you can see that particle may be small, may occupy only 1%. The wake looks so big, 10 times big. Each particle is creating wakes that are 10 times its own size. That's a lot of, they cover a lot of volume, and fluid is fluctuating, eddies are being shed. There's a lot of pseudo turbulence, and this is what I was talking about, is pseudo turbulence. Okay. Yes.
Related to that, so when we have a regime with a lot of particles, can we say that the pseudo turbulence plus turbulence would have a more of an isometric effect, and the big structures would not be there or be like ruined?
You're right that if pseudo turbulence is created, and there is also other sort of background turbulence is there, the presence of this turbulence will interfere and modify that. Sometimes it may reduce the other background turbulence, sometimes it may enhance it. A lot depends on the application. But
do we expect like a smoothing effect because of the particles?
see, that's the thing, is that the difficulty is that nobody can say universally yes, it's going to decrease, or yes, it's going to. So there is no such answer, and that's why multiphase flow is hard in the sense that the effect of pseudo turbulence on regular turbulence can be this way or that way depending upon whether it's a rocket flow or a fluidized bed or some other problem. So there is no universal answer, and that's probably why we are here. So I will skip the next topic that I wanted to cover, but I just want to say what it is. What makes, see, everything I said right now is doing a wind tunnel experiment. You putting your particle on a string and then send. But in reality what happens is that particle is moving. Imagine that you drop a particle. Imagine that you do a very simple experiment. You can think of a simple experiment, and the Reynolds number, let's say, is very small. It doesn't have to be quite Kolmogorov, even bigger than Kolmogorov scale. I mean, but with small particle, Reynolds number is not that big. It will fall vertically. In a quiescent medium, it will just fall vertically. Okay. Now, when it becomes one-sided wake around 270, I was talking about, is that it will be still laminar. It will just go to one side. Now, if it starts shedding vortices, well, maybe the particle may just go like this. Okay, every time it's shed. So in other words, particle is not like putting on a string and stationary. When you let it move, it's creating the wake, and it's sort of like dog wagging the tail, and the tail starts wagging the dog as well. I mean, that's a very complicated problem. Okay, so the particle is falling down, it's shedding vortices, and the vortices are shedding. You better move this way, this way, this way, and then the shedding changes, and the shedding change will change the particle. So you can sit there and say, oh my God, that's a tough. Maybe I switch over to electrical engineering. Okay. That's when you. So it's a pretty hard problem, right? I wanted to think about that this is a fairly complex problem. Also this nice sequence I talk about, like 270 this happened, 360 this happened, 3000, maybe everything is changed. Not only that, it depends on the density ratio. Somebody was asking yesterday or this morning, what about density ratio? Somebody asked, and that makes a big difference now. If you take a very dense particle, heavy particle like a steel ball, when it shed vortices will ask it to move, and it say, no, I'm too heavy and I'm not moving. So there, all the theory I said may apply for a steel ball falling through air, no problem. If the steel ball is falling through water, then the density ratio is maybe 13, 4, whatever that's. So it may respond, but you can immediately see that if you have a bubble in, bubble will go crazy because he has no mass, he is responding. By the way, I should also mention that added mass becomes very important for a bubble, because if you want to accelerate a bubble and you ask, I want to take a bubble and I want to accelerate, if it is in vacuum, I don't know what that means, but suppose there is a bubble in vacuum and you want to accelerate it, you hardly have to apply any force, right, because mass is nothing, and you have, but then the added mass, if you take a bubble in water, the force that you have to exert to accelerate the bubble is not the mass of the bubble itself. You have to accelerate the added mass has to be accelerated. So, that is something that I wanted to respond. But anyway, going back to what we are talking about is that when shedding starts and when the wake is becoming chaotic, now lighter particles will go crazy, and everything I said now you have to rethink. Okay? So I have said everything in this lecture is a very clean problem. You mount it on a string, the density doesn't change, you don't let it move, only you change the Reynolds number of the flow. But in a real system, when you have a multi-phase flow, all this is happening and happening in an even more crazy way. The vortex setting will keep moving the particle itself. Okay? So keep that in mind.
Sir, one thing to ask.
Yeah.
So right now we are having 3 types of lift.
Yeah. Yeah. So yeah, there is the rotational lift, shear induced lift, and self induced lift. The other thing, that's a great question. So when you think about it, in the morning we talked about a particle uniform flow or some flow. So in other words, we talked about undisturbed flow. Everything makes sense only at Reynolds number less than few hundred. Everything in the morning I talked about. Because like you point out here, even if the flow is uniform, we now start seeing that the force on the particle could be complicated because it's changing its own force by shedding vortices. Okay? So we never talked about this, and this is an open thing. This area is ripe for modeling. Very little work has been gone on modeling self-induced wakes, and the effect of the wake on the particle back effect is a very unknown. People don't know a whole lot, because most of the modeling, when you think about it, maybe because most of the application the Reynolds number is only few hundred. But when you talk about shock particle interactions or very high speed flows, etc., this is an area that has not been very well studied.